So welcome, Farid and Alexis, Alexia, Susanna, and welcome Erez, Stefani, Diego, Rigny, and Adam. Thanks for coming. Let's jump right to the quiz. Okay, so here's the quiz. And question 1 is determine if the following limit exists. Prove your answer is correct. Okay. If the limit does exist, state the value of the limit. Okay, so we got the limit as xy goes to 0, 0 of x plus y over x minus sine of y. All right. Do you think it exists or do you think it doesn't exist?
Depends along which one.
A limit either exists or it doesn't exist. It doesn't depend.
Oh, it's divergent.
Yeah, if it diverges, it does not exist, period. Yeah, there's no depending on with limits. They either exist or they don't exist. So if we think it doesn't exist, then we find two paths, hoping that we can get to different places. What's the easiest path that I mentioned a few days ago? Yeah, the axes. So let's start with, I don't know, the x-axis, positive x-axis. So let x equal 0. Sorry, x-axis would be x equal t. And y equals 0. So then we take a limit as t approaches 0. And if y is 0, we just get x over x, because sine of 0 is 0 also. And what is that limit? Yeah, that's, it's 1. That limit's 1. X divided by x is 1. Any questions on that? Okay, let's let x equal 0 and y equal t. So we take the limit as t approaches 0. And now we plug in 0 for x, you get y over negative sine of x. I'm going to pull the negative outside, just easier to type. Sorry, not y, yeah, t. And actually, the other one should have been t, not x. Everything becomes a t. So we get t, we get negative t over the sine of t. Do you remember what that limit is? And remember from calculus?
Is it -1?
Yeah, it's -1. So you have a couple choices. Either you could have it memorized, and sine t over t is 1, goes to 1. So t over sine t also goes to 1. The other, let me do it the fancy way with L'Hopital's rule. And if you use L'Hopital's rule, then we get the limit as, because, by the way, you plug in, you get 0 over 0. So that's why we can use it. T approaches 0 of -1 over the cosine of t. And now cosine of 0 is 1. So we get -1 over 1, which is -1. All right, so along the positive x-axis towards the origin, we ended up with 1. And along the positive y-axis towards the origin, we ended up with -1. So what's the conclusion? Yeah, the limit does not exist. D&E is the easiest way to type it. Any questions at all on the fact that it doesn't exist in the proof? Because I did ask you to prove it, and this is proving it. You show that two paths go to different places, and then you've proven it. Any questions at all on this particular question? Okay, so let's move on to the next one. So determine if the following limit exists, prove your answer is correct. If the limit does exist, state the value of the limit. So we limit as xy goes to 0, 0 of x to the fourth minus y cubed over x squared plus y squared. So what do you think? Do you think this one exists or not? Yeah, this one looks like it might, because notice the powers of x in the numerator are higher than the powers in the denominator, and y also. So that gives you a guess that it might exist. If you think it exists, then what was the technique that we had 2 days ago to show a limit exists?
Convert to polar.
Yeah, we convert to polar. By the way, you could use epsilon delta. That is brutal and miserable. You'd never have time on a 20-minute quiz. So polar is the way to go. So convert to polar coordinates. And when we do that, we have the limit as r approaches 0. And now let's plug in what we get. So x to the fourth is r to the fourth times the x is equal to r cosine theta. So cosine to the fourth of theta. Okay. I just call it t, so I'm going to type the whole word theta. And then minus y cubed, which is r cubed, times the sine cubed of theta or t. And then divided by, what's x squared plus y squared?
R squared.
R squared. That you're all supposed to know. So that's the limit as r goes to 0. When I divide, what does it become? We're going to have an r squared, because r to the fourth over r squared is r squared, cosine to the fourth of theta or t, minus, and the next term, if you take r cubed divided by r squared, we get r sine cubed of t, just like that. Okay. Now, it's very important that cosine to the fourth of t and sine cubed of t are continuous functions. And because those are continuous functions, that means we really can just plug in r equals 0 and see what happens. And what do you get? Equals 0. So this limit does exist and is 0. Any questions? Any questions on question 2? Okay, question 3. Find the largest region in the xy plane in which the following function is continuous. And we have f of xy is equal to natural log of y minus x. Okay, so to be continuous, what do we have to make sure?
Equation greater.
Okay, we have to make sure that that it's defined, right? First thing, if you're not in the domain, you have no choice. Okay, and so logs have trouble when they're non-positive. Any questions on that? So in particular, we want to make sure that the inside is positive. So we just take y minus x is greater than 0. Or y is greater than x. Okay. Any questions on that? So the answer is the set of all points, the largest region is of continuity is the set of all points so it's the set of all x comma y such that y is greater than x. That's all there is to it. Any questions at all? Any questions at all on the largest region of continuity?
Yeah, I have a question.
Mhm.
So in the homework, it was more like making you put it on a graph. So like if you think about this, can it be like y equals x and then above that line?
Right, now here's the thing, and this is very important, that see this greater than? Greater than and greater than or equal to are different. So the answer is you can do that, but you have to make sure that the line is dashed and not solid. Does that make
Okay,
sense?
yeah. That's what we were doing on there. So I kind of wrote that in words. I tried to write it in words.
Yeah, yeah. So yeah, I mean, the problem with graphically, it's too much of a pain to type.
Yeah.
To draw a graph in Canvas is like not possible. And that's why the homework and the quizzes have to look a little different, because the homework has that whole graphing tool. Canvas doesn't have a graphing tool.
Yeah, I was just curious if it was sort of the same thing. Thank
Yeah.
you.
Yeah, it's the same thing, but unfortunately the technology is weaker in Canvas. So I can't have you do it. Had the technology been there, I would ask you to do it, but I couldn't. So I tried to make it a similar problem, except that we don't have the graphing tool, so just describe it.
Thank you.
Okay, great. Any questions on the quiz? Any questions? Okay, it should start feeling like calculus again. Is it? Is this class feeling more like calculus instead of analytic geometry? Because we just did limits and continuity. And
I like the analytical geometry, though.
You like the analytic geometry? Sorry.
I think I liked it more than calculus.
Yeah. Well, we're doing calculus now pretty much for the rest of the quarter. We're doing the last few weeks, by the way, like 4 weeks probably, is tough. I just want to give you a warning. Sequence and series, a lot of summation notation stuff. Just a warning, and a lot of theorems and proofs. But right now we're moving into the feel of calculus. It should look very similar to what you did the first quarter of calculus. Whereas the last few weeks we didn't really feel like the calculus because it was geometry. And everyone has their favorites, what they like and what don't like. Okay, so let us move to the webinar's table of contents, and we are on Q&A. So are there any questions about a homework problem, about anything else that's going on with especially math? No more earthquakes, thank God. I don't know if you all felt them, but they were a little scary. Any questions? Always happy to answer questions if you have them. Okay. All right, if there's no questions, then I'll move on. Need to brush up on L'Hopital's rule. Yeah, that I'll let you know. L'Hopital's rule comes up just as you least expect it in this class. It's going to come up again in about a month. So once in a while, you get L'Hopital's rule. Okay. But since what we just finished, the quiz today was on limits, you shouldn't be too surprised that L'Hopital's rule is going to come up, because that was a big way of finding limits. But then we're moving on to derivatives, and then you won't need L'Hopital's rule anymore. Okay, and then it comes up again later. Okay, who remembers the definition of a derivative? Do you remember the definition of a derivative? That happened, in October, I think, if you had it here. I mean, here meaning Zoom with me. Who remembers the definition of the derivative? There's an x and an h, and you take a limit? Definitely. There's an x, there's an h, you take a limit as h goes to 0, and you look at the secant line, which is f of x plus h minus f of x, because that's the change in y, divided by the change in x, which is just h. And that's the definition of the derivative. Okay, and then geometrically, the derivative kind of tells you how steep up or steep down the curve goes. Okay, what is the slope of the tangent line? Well, we've moved on in this class. We're no longer restricted to living in a plane, which is good. I don't want to live in a plane. I want to live in 3 dimensions at least. At least that's what I can see, okay, in terms of spatial dimensions. And we want to be able to do derivatives. Okay, we want to extend the idea of the derivative that we had for functions of 1 variable to functions of 2 variables. Okay, hopefully you all agree that's something you'd probably want to do. So here's the big definition. And it's going to look very similar to what we saw in first quarter calculus when we had the derivative of a single variable function. There's still going to be an h. And here's one of the big difference. This is the big difference, is there's not one derivative. There's 2 different first derivatives. That's something you have to get used to. And the reason is we have 2 variables. So I'm starting with the 2 variable definition. And that is the following. The partial derivative. So very important that you get those down. Is that now we're talking about the partial derivative of f with respect to the variable x. Okay, so now you can't just use prime anymore, because you have to say, is it x or is it y that you're looking at? And the partial derivative of f with respect to x is the following. The first is there's different notations to use. And you got that in first quarter calculus. Remember you had a dy over dx versus a y prime, whether you're listening to Leibniz or Newton. Same idea with partial derivatives. We got the Leibniz way and we got the Newton way. And depending on, who, not just who you listen to, but some notations are better than others depending on what you're doing. And we'll get that throughout the course. So the first thing is we have this interesting symbol. Anyone know how to read that symbol? It's not a letter of any alphabet, by the way. In fact, I have no idea who came up and why they came up with it. Anyone know how to read that symbol? I don't know if you've ever seen it before. Okay, so that symbol, let me write this down. That one. Is said or spoken as del. I think it's pronounced the TH like theta. Looks like it is. No, it's del. Okay, so the way you pronounce that symbol is del. So this might be the first time you've seen it, and we're going to be using it a lot. So you want to get used to it. Okay, maybe it's the Old Norse alphabet. I have no idea, actually. Bruce would probably know. He's more of the math historian. So we write del f over del x. And what we're looking at is the del indicates that we're talking about a function of more than one variable. Because if you have a function of just one variable, then what letter to use? The hint is it's not what I just wrote. So what do you use before the f if f is just of one variable and you want to take a derivative? You should all know that one. Yeah, the d. Then it's df over dx. But if you're talking about functions of more than one variable, you use del. So del f over del x and is equal to, and what equal just means there's 2 ways of writing the same thing. The other way of writing del f over del x is f sub x. Okay, definitely eat less letters to write, but it doesn't show the fraction. And remember, derivatives are really fractions. They're kind of rise over run. And as we see in this definition, it's equal to the limit as h goes to 0 of f of x plus h comma y minus f of x y all over h. So that's the rise over run, but we're now running along the x, parallel to the x-axis, because notice that we are moving x a little bit and we're not moving y at all. So y stays y in the numerator's two terms, whereas x, we're looking at what's the difference between the point you're looking at and then move a little bit horizontally, and that's what we're looking at. We're moving x a tiny. We're not moving y at all. And that's why we use del f del x, or f sub x. So this is the formula for the partial derivative of f with respect to x. And then once you know with respect to x, with respect to y is kind of obvious. The partial derivative of f with respect to y is del f over del y, or f sub y. So now we just use y because we're emphasizing and saying that we're moving along now the vertical axis. And we take the limit as h goes to 0 of f of x y plus h minus f of x y all over h. So those are the definitions. Okay, and what this means is you're keeping one variable fixed and slightly moving the other and looking how much the dependent variable changes in a ratio to how much the independent variable changes. It's really the same idea as the derivative of one variable, but what's happening now is you're saying, well, we're just gonna like hold the other variable fixed. So if you do del f over del x, we're gonna hold y fixed. We're gonna pretend it's not even a variable. We're not gonna move it. And we're gonna look at what is the derivative as you move x. Any questions on this definition? Any questions? Okay, so let's use the definition to find some derivatives. Okay, so here's the example. We want to find del f over del x and del f over del y for f of xy equals 2x minus 3y. So I'm going to do del f over del x first. And what I'm going to do, I think is the easiest, copy and paste. So there's our definition. Then I could write down equals. And I'm going to copy and paste this part too. So we're going to have a limit as h goes to 0. And now it's f of x plus hy. So I'm going to write down what f of x plus hy is. That's going to be 2 times, well, I'm replacing x with x plus h. X plus h. And y I'm keeping the same, so minus 3y. Any questions on writing down what f of x plus hy is? And then I do minus f of xy. So I'm going to do something on purpose. F of xy is just 2x minus 3y. What's wrong with what I just did? And it's very important, and it's the number one mistake I see in using the definition of the derivative.
You didn't distribute the minus to the entire function?
Yeah, I didn't distribute the minus. I didn't put parentheses around the f of xy. So I wanted to kind of emphasize that because that's the mistake I see mostly. Any questions on that? Okay, now the rest is, most of the rest is algebra. So let's do a little algebra. Well, 2 times x plus h is just 2x plus 2h minus 3y, and then you get a minus 2x plus 3y all over h. So basic algebra. And now let's do more algebra. So we have 2x minus 2x. That's gone. Those disappear, cancel each other out. We have minus 3y plus 3y. And those cancel. Now, what's the limit as h goes to 0 of 2h over h? Very easy. That's equal to 2. So that means the partial derivative of f with respect to x is just the constant 2. Any questions on that? Any questions? Okay. What I'm going to do, I want to give you a couple minutes. It shouldn't take too long. Let's see if you can do the second one, del f del y. So I want to give you a couple minutes to try it. I want to make sure you can use the limit definition of the partial derivative of f with respect to y, and see if you can do that. And it's similar, it's not exactly the same, but do it on a pencil and paper. And then when you're done, write down what you got. You don't have to show all your work, in your chat box, because that would take forever. But make sure you show all your work on a piece of paper. And do your best. And the hint is it'll look real similar to what I just did. So I want a few of you to put an answer in. Okay, good. The answer is -3. And hopefully you took a limit as h approaches 0 of f of x comma y plus h minus f of x comma y all over h. And then substituted in, did some algebra, and came up with -3. So let me ask you something. Is there anyone that needs to see me do it? So I was really hoping you'd all do it, because it's pretty easy once you know how to do it. But, put in the chat box, please show me, or put in the chat box that I got it, one or the other.
Can you show us how to type it?
Okay. Well, the one thing is you don't necessarily need to know how to type it the way I'm typing it. And that is because I'm using Google Docs. So really it's how to type it in Canvas, right? That you need?
Yeah, because I feel like that might take a while. Like, obviously not this wouldn't take that long, but I would see how, like, if you were to give us a problem.
Yeah, so you need in Canvas.
How long it would be to put that many variables.
Yeah, well, the first thing is, and hopefully you got it in terms of my rules, as long as you're communicating, I'm okay for
the math
quizzes.
I understand. It's just the typing. I don't want you to get confused when you're reading my work when it's typed.
Right. So let me show you how you would type it, probably on a quiz. There's two things. There's one is typing it so that you can show me that you know what you're doing so I can give you credit on a test. And there's the other kind of typing, and that is typing so it looks beautiful. Okay. And they're very different. If it looks beautiful, it takes a lot longer and, harder to do. And it's hard. You have to go back and forth from the question. But if I just type in limit, and then I'm going to go h, and then I put a little dash and a little greater than sign to make it look like a goes to. That's how you make a like simple arrow without using any fancy stuff. 0. And then I would do, let's see, the function was, let me remember again, 2x minus 3y. Where are we? That one. So we're going to have 2 x plus h minus 3y, and then minus, and then now we're going to do 2x minus 3y without the plus h. So we're going to have 2x minus 3y, close the bracket, and then divided by, I like to put spaces to make it a little easier to see, h. Does that make sense? Is that what you wanted to see?
Yeah, that's great. Thank you.
Yeah, so nothing fancy, and I don't expect you to do fancy. I mean, I could teach you how to do fancy too, but that won't help you on an exam. It will help you if, say, you become a researcher, you know, and then you have to publish something with, you know, pretty font and all that. But that's totally different. Or if you become a teacher, then you'll need to learn how to type. So, for example, you know, I put fancy stuff. I made it look pretty up here. Okay. So it looks like I didn't see any requests to see how to do it because it's not hard. Okay. Do you think these could get hard?
Absolutely.
Yeah, and they can get worse than hard. They can get brutally evil, so you would never ever want to do it this way. Do you believe me?
Yes.
If I did the same thing, except instead of 2x minus 3y, if I did something like e to the negative cosine of x squared minus xy plus y, this cube root of y, good luck. Good luck doing it with this limit definition. Okay, you're going to need huge amounts of algebra. It is going to be pages and pages long. Okay, all right, so the answer, the answer is -3. Yeah, the answer is -3. Yeah, had everyone gotten it wrong, I would have said something. Yeah, the answer is definitely -3 for the partial with respect to y. Okay, for this one, it makes sense that you would say -3 just from looking at it, because this is, you know how to find the derivative in one variable if it's a line, and that is just take the slope. Well, what is it? This isn't a line. There's 2 variables. What is it? What is the surface? In one word, it's not a line. So what do we call f of xy equals 2x minus 3y? In one word? In terms of what the surface looks like? That you're all supposed to know because we did that, weeks ago. Yeah, that's called a plane. Okay, that's a plane. Okay, so we call that a plane. So similar to a line, when you have something linear, and this is linear, then the derivative is just going to be the coefficients. But as soon as you leave linear, especially when you get into messy, you're not going to want to do it this way. So here's, I'm not going to give a proof to it. The proof would take too long. And I want to make sure you know how to take partial derivatives. So here's the easy way. And that is to find the partial derivative with respect to a variable. Imagine that the other variable or variables, if you're doing multiple variables, like 5 variables or something, to be just constants. And then find the derivative of the function, considering it as a function of just that one variable. Because you know how to find a function of one variable. Okay, that you're taking the partial derivative with respect to. So here's an example. And the example is find del f over del x and del f over del y for f of xy equal x cosine of x over 3y. Okay, Do you think you want to do this one using the limit definition?
No, it would be too much work.
Yeah, and I don't know if you know, which one do you think would be worse? One is much worse than the other. Any guess on which is worse? Del F del X or Del F del Y? Okay, your guess is Y, but it wasn't right. Del F del X is much more evil. Okay, and you could trust me on this one. If you had to do del F del X, you're going to have to use all kinds of trig identities with sum of angle formulas and all kinds of other algebras. This would be probably your complete nightmare. Okay, Y actually is not that bad. You could do, if you knew what to do, you could do Y in about 5 minutes, but X would probably take hours. Just to let you know, this would be absolutely evil if I said find the partial derivative with respect to X using a limit definition. On the other hand, if we do it the easy way, this is not bad at all. So let us do it, and I'm going to do it with notation now. And that is del over del X. So I'm going to do one at a time. I'm going to do this one first. Of the fraction X cosine of X over 3y. So let's start with that one. And what I'm also going to do is make it bigger. One thing about Google Docs is it doesn't do a good job of making fractions big enough to see. Do you agree? So I like to make it a little bigger. All right, so now based on my little suggestion is what we're going to do is we're going to say, well, y is treated as a constant. Do you agree? That's what the easy way is. Well, if y was a constant, let's say it was, I don't know, 47 or something, what would you do to take this derivative as a function of one variable? What would your first step be? Any thoughts? So now we're base.
Isolate.
When you say isolate, what do you mean?
Oh, like move the variable to one side.
Well, we only have, I mean, it's just, there's no sides here. It's not, we don't have an equal sign, right? I put an equal, but there's no equal sign here.
We use substitution.
That's taking an integral, not derivative. Yeah, substitution was for integrals. So if you have a constant down here, you can pull constants out. Do you remember that? Constants can get pulled outside the derivative. And that's what I'm going to do. I'm going to pull that over 3y outside. And what I get is equal to 1 over 3y and then times the derivative with respect to x of x cosine of x. And the idea here is we're really treating y as a constant. So this is a function of one variable, and that's why you want to think about it. How do you find the derivative of x cosine of x? What do you have to do calculus-wise? Yeah, product rule. And that's not too bad. Well, the derivative of x is 1, so I just get cosine of x. And then plus The derivative cosine of x is negative sine of x. So I'm going to make that a minus x sine of x. That's it. I'm done. Isn't that nice? Any questions at all on finding the partial derivative of f with respect to x? Any questions? All right, I'm going to do what I did last time. I'm going to have you see if you can get the partial derivative of f with respect to y. Give it a shot, spend a minute or two, and see how you do. And while you're doing that, I'm going to type in another example just for fun. So let's see if you can find the partial derivative of f with respect to y. It's not that hard if you know what to do. Okay, let's see if a few of you did it. Negative x cosine x over 3y squared. I see a negative 3y to the negative 2, x cosine of x. Okay, just to note, the negative 3y to the negative 2, the negative needs to be pulled outside the parenthesis, not inside. Does that make sense? Rigney? Yeah. So it looks like you got it. Do you need me to show you how to do that? Anyone need to see how to do it? Since I did one example for you.
Can you just write out the answer?
Sure. So del f del y equals, and we still have the x cosine x. I like to just pull it out. And then we have, there's a 3y to the negative 2. Sorry, negative 1. So that's going to give you negative 1 times 3y to the negative 2. That's it. There's no work to show really because you're pulling out the x cosine x. I guess you could write it as a x cosine x, 3y to the negative 1. Write that step in.
I wrote it as a fraction. Is that okay?
Yeah, that's fine. You know,
I
my
didn't
rule,
like negative exponents. That's why.
yeah, you know, my rule is that as long as it's correct, I'm happy. Whether you do more algebra, that's your choice. All right, so now I have a problem that looks really evil, but is it? Okay, so find del f del y for f of xy equal xy minus x times a tangent of e to the secant cubed of x to the sine of x minus x squared over x cubed cosine of, oops, just a mistake, 3x minus 5. That's what I want. How do we get the derivative with respect to y of this? What do you think? I wanted to write one that
Yeah,
looks right.
it's that whole mess on the right there is all x's. So we just treat that like a constant and just work on the xy.
And what's the answer? What if I just asked you for ay plus b and said, what is the derivative with, what is the derivative of that? It'd just be a, right? Well, in this case, the a is x. So the answer is x. Okay, so it may look evil, okay, and I wanted to make it look evil, but this turns out to be a really easy problem to do. Okay, if I change this del f del y to del f del x, then you just would start crying. Sound right? Because then this really is evil. And I wouldn't do that to you. That's too evil. But if you want to find the derivative with respect to y, we can do it. Any questions on this example? Okay, so let's look at pictures. All right, so remember contour maps. Contour maps make it really nice for visualizing the derivative. So if the level curves are close to one another in the direction of the variable that you're considering, then the partial derivative with respect to that variable is large. And it might be large positive or large negative, depending on whether you're going, whether it's increasing or decreasing as you move along the x, parallel of the x-axis or parallel to the y-axis in the direction. So positive x or positive y. Okay, otherwise it's small. If the level curve at a point is horizontal, then del f del x equals 0. And if the level curve at the point is vertical, then del f del y equals 0. So let me show you some pictures. I think the best way to do this is actually give you examples. And this is something, this is what I am looking forward to when we're done with this class. You know what I'm going to be doing a lot of? Not math, by the way.
Hiking.
Yeah, hiking and particularly backpacking. So here's my favorite place to go backpacking. Have you been here? Anyone been here before? Got Lake Aloha, Pyramid Peak, all kinds of beautiful places. And this is a contour map of my favorite place on Earth. Okay. And my favorite place to backpack is Pyramid Lake. You see that right here? I usually backpack right around there. It's a really good spot. You put your tent right there. And then what I like to do is I like to hike to Pyramid Peak. Okay, so maybe I'll walk over here first just to make it a little easier to talk about. So if you hike to Pyramid Peak and you look along the trail that you're hiking, so let's say I pick a point near Pyramid Peak, near Pyramid Lake right here, and I look at the partial derivative at that point with respect to x. What do you think it's going to be? What's your guess on what that might be? So I'm right next to the lake, hanging out with my tent right here, or maybe here. And what do you think that partial derivative might be with respect to x?
0 because of sea level.
Well, it's definitely not sea level, but lake level is what you really meant, right?
I mean, like lake level. Yeah.
Yeah.
It
This
looks
is
relatively smooth. That's
yeah.
why.
It's nowhere near sea level though, but it's near lake level, and in particular, if you go a while, it's going to take a long time to hit a contour line. Okay, it won't quite be 0. Okay, but it might be point, say 0.2 or something. Okay, and in fact, it's going to be negative 0.02 because remember, the positive x-axis is due east. Does that make sense? So if you take one step due east, you're going down to the lake a tiny bit, and it's going to be down, which means you're going to have like a negative maybe 0.01. Any questions on that? So it's a good place to put a tent. Very, very slight decline as you're looking east. Any questions on that? All right, now you'll notice, by the way, that my tent over here is maybe not even a mile from Pyramid Peak. Easy hike or not easy hike? Just hiking a mile? What do you think? Yeah, if you did this, you'd probably die. Just let you know that. And let me explain why you would die. Okay, let's say you got to this point here, this contour line at 9,000 feet. What's going to happen if you step one step due east? What's going to happen?
You're gonna fall off a cliff.
You're going to fall off a cliff. So what is the partial derivative of f with respect to x?
Probably something negative.
But is it like negative 0.01 like the other one was?
No.
Okay, definitely not negative 0.01. It's going to be like negative 30. Okay, because it is like a cliff right there. Okay, and I don't know if any of you have done this hike. It's a wonderful hike. It's called switchbacks. You go back and forth and back and forth and back and forth, and you got to jump one little step and then back and forth. Okay, and you do those switchbacks like that. Now, what about this point? What is a partial derivative at this point, right here, say, with respect to y? What do you think? So I think you can see my cursor, right, where it is on that 9,000 foot contour line. What's a partial derivative with respect to y? Because we already found the partial with respect to x was like negative 30. It's going to basically drop off the cliff. Yeah, partial with respect to y is 0, because if you take one step forward, you're on the same contour line. You haven't moved up at all. So if you look at the rise over run as you go due north, there's no rising. You're on the same contour. So that means the elevation is the same. So due north, you have a 0 elevation gain. Or in other words, a partial derivative with respect to y is 0. And that is, by the way, why you do switchbacks parallel or close to parallel to the contour lines. Because if you do switchbacks close to parallel to the contour lines, you're never going up that much. Does that make sense? On the other hand, if you just did that direct route to Pyramid Peak from Pyramid Lake, you better have equipment. Never going to happen. That's serious rock climbing. Any questions on this idea? Any questions? Okay. If you haven't been here, I strongly recommend it, by the way, but only if you're hardy into serious hikes and backpacking. You gotta be in good shape. Let me give you another example, another application example. And this is from NOAA. Okay, NOAA, the weather report. And have you seen a map like this before?
During hurricane seasons.
Yeah, what do these numbers mean? Do you know what they represent? Yeah, they're pressure. Isobars, these are pressure. And in fact, it's funny, everyone has their own name for contour lines. The name they use for the contour lines when you're talking about a weather map like this, anyone know what they call these? There's a word for these lines. The lines of isobars, constant isobars. Okay, it's just some weather words. All right, so now, first thing, let's go to Tahoe. Tahoe's over here. Hopefully you all know that. The great thing about Tahoe is it's really easy to find on a map of the United States because it's right here where it hits. All right. So what do you think? If you take the partial with respect to X or Y, what do you think that's going to be? Is it going to be big or small in absolute value? What do you think? So this is an example of using what we're doing to understand weather. Yeah, it's small because if we take a little step over due east, the partial with respect to the X is not really changing much. How about due north? Still not changing much. Okay, and I'm not sure if you know about this, but do you know what it means? Let's say you're going to go over, let's say you're going over here in, I'm not great with geography. How about right, let me find a good spot. Okay, so if you go in Texas, for example, now if you go due east, what's happening? Yeah, now you're going to have if you take a step due east, there's going to be a pressure change. And that means the partial derivative with respect to X at that point is going to be positive. Do you see that? Definitely higher than in Tahoe due east. Okay. And let me grab this point. I think are we in Canada yet? Now we're in Canada. And let's say the partial derivative with respect to Y. What do you notice now? Large or small? Yeah, very large. Now, do you know what that means weather-wise? So if you have a high partial derivative with respect to Y, yeah, not change in wind, just wind. Wind. So what you're going to have is you're going to have a, in this case, a southerly wind because we're going from high pressure to low pressure as you go south. So the way you do weather reporting and weather predicting, meteorology is what you look at, is you look at the partial derivatives with respect to X and Y. And we're going to learn about, you can do this with any direction, it turns out. And if that partial derivative is large, you're going to have a wind area. And if the partial derivative is small, like say over here or even Tahoe, then it won't be windy. Okay, so if you got to change from high pressure to low pressure, you get wind. Any questions? Any questions on this application? And I really like this because it's like, this is one that we all can feel wind. If you've never felt wind, then your parents need to be punished because you've been trapped inside all your life. Okay, so this is why wind happens. It happens because the partial derivatives are high when you're looking at the function, not elevation function now. Now we're looking at pressure as your function in X and Y. Any questions on this example? Okay, and by the way, this is today's weather forecast. So good day to go kayaking because not much wind unless you want to go kayak surfing. Base is going to be calm, easy kayaking. Okay, wear a life vest, by the way. Any questions at all on that? Okay, so that's contour maps. Okay, so just a note For functions of several variables, so if you have 5 variables instead of 2, nothing changes. So here's an example, and I'm just going to do it by example, and I think you'll agree, nothing to worry about. You want to find del f del u for f of u, v, w, x, y. So a function of 5 variables is equal to x e to the wy minus u tangent of v minus w. And we want to find del f del u. Any thoughts? And the hint is it's pretty easy. It's really easy, actually. See if you can put in the chat box what you think the answer might be. Any ideas? The idea that it's not hard. If you're finding it hard, you're doing it wrong. You use the same process that we just used with 2 variables. Now we have 5 variables instead. It doesn't make it any harder. So you can put in the chat box what the answer is. Good, good. Okay, so let me walk you through it. So first thing, there's 2 terms. We have x e to the wy. When you're taking the derivative of that term, what do you get if it's with respect to u? Just for that term. Yeah, that's just going to give you 0. There's no u in it. So it's a constant. X, w, and y are all constants. So is e, by the way. So that just goes away. So really all we have is this u tangent, the minus u tangent of v minus w. Well, in this case, v and w are constants. Tangent of v minus w is a constant. So that's the same thing as what is the derivative of negative a constant times u? And that's just negative a constant. So the answer is delta f del u. Is equal to negative tangent of v minus w. Anyone lost on that? Okay.
So on a test, can I like skip some steps of writing?
Yeah, here's the thing. If you show your steps on a test and you make a mistake and your answer's wrong, then I can give you lots of partial credit. If you don't show your steps and your answer's wrong, I can't give you partial credit.
Would it be smart if I just like wrote my answer, like wrote the main steps and then went back if I had extra time to fill in the...
And that could work, yeah. But you want to communicate your thought process. That's the most important thing.
All right.
Yeah, you want to communicate your thought process so I can get partial credit if you
maximize the points.
Yeah, if you make like a little mistake, like you lose a minus sign, because if you lost a minus sign and you have no work shown, I can't give you points. Does that make sense?
I just don't like typing math.
Yeah.
I think my problem is that I don't like typing the math. I like writing it.
Yeah. Well, writing is fine. Writing is fine as long as you're communicating. Okay. What if instead of del f del u, what if I asked you to find del f del w? It's a little harder, but not too bad. I just want to give you an example. Okay, now they both have w's in them. How do we take the derivative of x e to the wy with respect to w? What rule do we need? That's a hint.
Is it chain rule?
Yeah, we need the chain rule because we got to take the derivative of the inside, and the inside is wy, and the derivative of wy with respect to w is y. We still have the x, that's a constant, so I'm going to write xy and then e to the wy. Any questions on that? Okay, what rule do I need to use for minus u tangent of v minus w with respect to w? Chain again. Okay, because we have an inside. The derivative of v minus w is -1 when it's respect to w. So I get a -1 times negative, so that makes it plus. We still have the u. See, if you remember, what is the derivative of the tangent function? Yeah, secant squared of v minus w. Figured I'd show you one that's a little harder. It's not evil, but there's a little work to do. Any questions on this? Okay, quick definition is higher order partial derivatives follow the same idea as higher order derivatives. So if you write f xy, that's del squared f over del x del y, and that just means take the partial with respect to x, and then take the partial derivative of what you get with respect to y. Or in other words, del squared f over del x del y is equal to del over del y of del f over del x. It's a lot of symbols and messy talking. It's much easier to see an example. So let me do an example. So let's look at find all second order partial derivatives of fxy equals x squared e to the xy. Okay, so the first thing is, how many second order partial derivatives are there? How many of them are there?
In this equation, I think just one.
Definitely not just one.
Two.
Not two. There's 4. So let me go through them all. Okay, there's technically 4, and we're going to find out 3 matter. So we're going to have f sub xx. So that means we're going to take the derivative with respect to x and then the derivative with respect to x. Okay, and that is equal to x squared e to the xy I need doubles sub x sub x. What that means is I first take the partial with respect to x, then I take the partial with respect to x again. What rules do I have to use to take the partial with respect to x? Yeah, product and chain. So that is going to be 2x e to the xy plus, and then it'll be x squared times y e to the xy. Okay, sub x, because I just took the first partial. And this is one of those where it's worth simplifying, because I got to take another derivative. So that is equal to 2x plus x squared y e to the xy. Sub x. Anyone lost so far? So I just took a first partial with respect to x. Now what do I have to do? Any thoughts? Yeah, I take another partial. So I take a partial of what I just got. And that's, again, product and chain rule. So it's a bit messy. I decided to do one messy one. Okay, so we take the derivative of the first, which is just 2 plus 2xy, with respect to x, of course. So 2 plus 2xy times e to the xy plus the first, which is 2x plus x squared y. And now I need the chain rule. Derivative of e to the xy is y e to the xy. So I'm going to throw in another y there, and multiply the y through, and then I get a y squared e to the xy. And there's my answer. Any questions on that? Okay, that was fxx. What else is there? I told you there were 4 of them. So what's another one? I just did fxx. Yeah, fxy. Okay, and now we're going to go to respect to x, and its derivative with respect to y. And, well, the good news is we already did the derivative with respect to x, so I can just copy and paste. Change that x to a y. Any questions on that? And in fact, it does help to have that. I'll just pop it right in. I forgot the equal. Change that to a y. Do I need the product rule? Okay, and the answer is yes. We still need the product rule. The derivative of 2x plus x squared y is just x squared. And then times e to the xy. And then plus the derivative of e to the xy is y, is x e to the xy. So we get a x cubed, we get a 2x squared plus x cubed y e to the xy. Any questions? What do we have to do now? We just did fxx and fxy. What else can we do?
There's such thing as fxx squared.
X squared is not a variable. Fyx, there we go. And I am going to do this. Actually, let's do it on this side. So what happens when you start running out of time? And I'm going to let you know that when you switch the order, you don't change anything. And I'll show you a theorem in a moment on that. I'm not going to prove it, but There's a theorem. As long as you have a nice function, in other words, no weird stuff going on, and it's very hard to come up with one that doesn't work. Okay, it has to have all kinds of issues. That fxx and fyx, fxy and fyx are the same. Isn't that nice? Okay. On the other hand, we need to do fyy. And that means take a partial respect to y and then do it again. So the first one, I don't need a product rule. I'm just going to have x cubed times e to the xy. I did need the chain rule. Any questions on taking the due respect to y? And now I take another due respect to y, and again x to the fourth times e to the xy. And that's it, I'm done. Okay, so I did all four of them. Let me let you know the big theorem. And that is taking higher order partial derivatives is independent of order for all nice functions. So for example, fxy equals fyx. Okay, so technically there's four different derivatives, but if you switch, you always get the same. A lot of times people will put them in a matrix, a 2x2 matrix for two variables. For three variables, you can have a 3x3 matrix. For four variables, you'll have a 4x4 matrix. It gets messy and big fast. Just let you know that. Any questions about this theorem? And this works for, you know, however many higher order you want. Okay, then quickly, because we don't have much time, I want to give you some very important examples that you've probably heard of, but maybe never saw. Have you heard of Schrodinger's equation? Okay. Okay, so that's the easy question. I expect a lot of you to say yes. What is Schrodinger's equation? Have you seen Schrodinger's? Here it is. So this is a major equation. And again, I'm not solving this, but this is Schrodinger's equation. I want to read it because that you should be able to read. Okay, I. Remember what I is? Anyone know what I is? Yeah, square root of -1. H. Anyone know what H is? H is a universal constant. I don't have time to get into all the physics of it. H is a universal constant, and then del over del t of capital phi of xt. So a partial derivative with respect to t of phi of xt. It's actually h bar, not h hat, but good try. Okay, of phi of xt is equal to negative h kind of barish. You call it hat? I've always seen it, maybe because I do physics, not chemistry. Squared, although chemistry was my minor, but I did more physics. Over 2 times the mass times the second partial derivative with respect to x both times plus v of xt times del times phi of xt. So this is called a partial differential equation. Do you think this is easy to solve? Okay, absolutely not. By hand, no. And by the way, even by computer, no. We could do it if you wanted to get perfect solution by computer. We could do it for hydrogen. That's about it. Okay, and it gets too hard after that. So this is brutal. I'm not going to get into what it all means, but I will tell you this is Schrödinger's equation. Okay, and if you get into advanced physics and chemistry, then you'll get into it and you'll get into the depth of it. Then there's the heat equation. That's the old, you open up a window And then you see what the temperature is. Then del U over del T equals alpha times the second partial of U with respect to x squared plus the second partial of U with respect to y squared plus the second partial of U with respect to z squared. And that's called the heat equation. And that, notice, is also a partial differential equation. Easier to solve than Schrodinger's, but still tough. So we're out of time, but I wanted to give you examples. And let me stop the recording.